So, but we're not going to have lab next week on Friday. I don't know what Max is going to do. I'll talk to him on Friday. One of the 280 lab TAs is just going to have an office hour during lab time in case you want some extra help. The Lab 04 pre-lab is due this Friday, and we will start working on the cross-section part of Lab 4. If you get through drawing the cross-sections, that's a good break point because the next activity is completely different. That is drawing schematics from layouts. Homework 7 is going to be due on Tuesday, and that's just because we got a little bit behind and I wanted to make sure I covered the material before the homework was due. But everything, then I can leave the schedule alone for the rest of the semester. Lab 4 will be our last lab. It will be 4 weeks in a quiz, so 5 weeks. Yeah. And the exam is on Thursday, March 25th. If you need to do the remote exam, just send me an email and we'll set up a time where it's agreeable to both of us. It's easier doing that through email than having a bunch of people trying to rush me after class saying when you can do this. So just send me an email. Dr. Cambeau is going to come in on March 30th and talk about the technology it takes to get down to 3 nanometers and beyond. It's a pretty interesting talk, and he worked in the industry and really knows what he's talking about when it comes to stuff like this. I worked at JPL. That wasn't really an industry, although for some professors they call it industry experience. No, it was engineering playpen experience. I've talked about the Accelerated Master's Program. Exam 2, what it covers is the parts of Chapter 5, 7, and 8 from the 6th edition. There's a cross listing on my, between the 6th, 7th, and 8th editions in my BB Learn. The 7th edition, it's Chapter 5, 8, and 9. They added an extra chapter into the 7th edition. I think that's still there in the 8th edition. Pretty much the same material. Again, the exam review should already be posted. Take a look at that. Look at the solutions for that, the lecture slides, the homework and the solutions. It's all amplifiers. 2 note sheets, 1 sign from exam. I forget the signing part. You just get 2 pieces of paper, and I won't look at them, so it doesn't matter. I'm not signing note sheets because I can't do it over Zoom. Trying to make it as evenly playing field as I can. So the things we've done so far, we've looked at the small signal analysis. Remember, the total signal equals the DC signal plus the AC signal. The first step of all these is calculating the DC bias point. And these are the big ID, big VGS, and big V out. One or VD, whichever one you need. You can use those DC parameters to calculate GM and little RO. And little RO is a major component in big RO. And when we want the gain for either a common source, a cascode, or a diff amp, the workhorse amplifiers for getting gain, the gain is GM big RO. And the common source has a negative sign in it. So the 3 things we always want to find for any amplifier are the voltage gain, the output resistance, and the input resistance, because with those 3 numbers, we can build this basic circuit model, stick the circuit model up 1 higher level of abstraction, and figure out what the gain is of my overall signal chain that includes this amplifier. That chart, yes, we need to use that chart. The one that tells you what is the input resistance looking into the drain, what is the input resistance looking into the source, and looking into the gate, it's always infinity. There is a chart that tells you the gain of a common source with source resistor, common gate and common drain amplifier. That might be handy to have on your note sheet. The IC amplifier part, when we're dealing with cascodes and common source and diff amp, these all have the same basic gain. It's GM big RO, and common source has a minus sign. So you're going to be careful, you know, which one's negative and which one's positive. And then these multi-stage amplifiers. If I take several of these models and I put them in series, can you figure out how to put that diagram together for like a 3-stage or a 2-stage amplifier? Because that's kind of like the big picture of what we're doing since exam 1. Okay. So where we're at on here, we've looked at the basic gain cell, we've looked at the cascode. Most of today is going to be talking about IC biasing, aka current sources. How do I get the right current and voltage to my amplifier so it will be in saturation and I will have either a linear gain or I have lower power? And we'll talk and give a few examples of those. This is the basic gain cell. In this case, this is a common source, but it could be a cascode, and it could be a diff amp. I have to supply some current to this. And in the 03 slides, our current source was basically a resistor up to VDD. And in these slides, and when we're talking about integrated circuits, instead of that resistor there, for a current source, I'm going to use a PMOS transistor to steer the current into, and that'll be connected somewhere, to steer the correct amount of current into that common source amplifier. It will both drop voltage and provide current, just like the resistor. It drops voltage and it provides current. So those are our 2 forms of current source. We found out that the transistor has a higher output resistance, so you can actually get a bigger gain with using a transistor than you can with resistors. Yes, resistance is futile. That was a perfect spot for that. Now, calculating GM and RO, at least once a semester, somebody tells me that, oh, I can't calculate GM. You didn't give me enough information. I don't know what KN is. Or I don't know what ID is. If you don't know what KN is, you could use this part of the equation. If you don't know what ID is, you could use this version of the equation. If you don't know what V over voltage is, you could use this form of the equation. It's important to have all 3 forms there. Part of the reason why I can never remember the equation for GM, and I always look it up, is because I don't know which one's going to be the easiest one to use on any given problem. Finding the output resistance, it's the early voltage over ID, which is, and the early voltage is in volts. VA prime is usually given in volts per micrometer. L is the length of the transistor, but a lot of times L is given as a number like 5 lambda. So you have to look up lambda. That lambda that we're talking about here is in micrometers. Another way you could calculate RO is 1 over lambda ID. This lambda is in units of per volt. When in the exam review slides, there is a picture of what the information is you get on the front page of the exam. And I either give you VA or I give you lambda. I give you one of these two. And I think it varies from exam to exam. be careful and know which lambda you've got, and you know by looking at the units of lambda. Okay. This slide is really important, and there's going to be at least 3 or 4 problems on the exam out of 5 of them that understanding this slide will be a kind of the key to really digging into the problem and getting more than the half of the easy points. Looking into the gate of a transistor, the input resistance there is infinity. Looking into the drain of the transistor, you get the RO times 1 plus GM times the resistance on the source, whatever resistance is there. And that's probably the RO of another transistor, or it's 0. Where these equations came from is somebody took the small signal model of a transistor with the dependent source and the RO in it, and they found the Thevenin equivalent resistance looking into each one of those terminals. That takes me about a half an hour of actual thinking to figure out every time I do that. So instead of doing that over and over again, if I use this chart, I've got a shortcut, a big shortcut. I don't have to do that small signal analysis and find the Thevenin equivalent resistance. I can just use this formula. Looking into the source, I see 1 over GM times 1 plus whatever resistance is on the drain over RO. Now let's look at this and think, just compare these numbers. If I don't have a source resistance and I don't have a drain resistance, the one on the left is okay. Looking into the drain, I see RO. Looking into the source, I see 1 over GM in parallel with RO. And this is approximately equal to 1 over GM. These are typical numbers here. GM's 300 microamps per volt, RO's 500 k ohms. GM is a transconductance. So if I take 1 over that, I should get a resistance. And so this is why this looks like a resistor here. 1 over GM, if I do the calculations, comes out to be 3.3 k ohms. That's a heck of a lot smaller than the 500K. So if I put them in parallel, I'm going to get basically 3.3 k ohms. That's why that works. Yes, RO is much bigger than GM. Much bigger resistance looking into the drain of a transistor than looking into the source. And if you want to make RO big, it's better to look into the drain. So let's look at this big mess. This is a review. We were looking at these calculating output resistances last class. So first thing I have to do is take this circuit and get the small signal model of it. This is the AC version of it, the AC circuit. Drawing AC and DC circuits generally end up on exam 2 also. So remember, for AC, our capacitors are shorts. So I can just block that one out, and I can block that one out. Our DC sources get shorted out, so this one becomes ground. This is just ground. VSS is also going to be ground. I think that's pretty much all I can do here. So that really helps us finding those equivalent resistances too. If I start with and we're looking for the AC RO, not some kind of impedance or anything like that. It's just basically when we're talking about big RO, that is an AC equivalent. What resistance? So I can block out my capacitors. So REQ1 is the resistance looking this way, And now this is pretty straightforward because I see RD to ground in parallel with RL to ground. So REQ1 is just simply RD in parallel with RL. Okay. REQ2 is the resistance looking into the source with a source resistance of REQ1. So REQ2, if I put my hand on my screen, I can almost write normally. REQ2 equals 1 over GM2 times, and I'm just referencing this formula over here, 1 plus the resistance on the drain is REQ1, which is RD parallel RL, over the there's no 2 transistor in here, it's just GM, over RO. There's only 1 transistor. So that is the resistance looking into the source. Define the resistance looking into, that's REQ2. We got to find the resistance going the other way. Oh, no, REQ3. We're going to do this one first. REQ3 is whatever REQ2 is in parallel with RS. I'm just going to write like that, so I don't have to write the expression for REQ2 again. You could calculate REQ2 and then just put in parallel if you needed REQ3.
REQ2, that's RD in parallel with RL.
Yes, RD in parallel with RL is what it says on the top. Okay, so now we need to find REQ4 and REQ5. They're looking in the other direction. So now REQ4 is looking into the drain. So it's going to be, oh great. The RO of that transistor times 1 plus GM. Okay, what am I doing? GM times whatever resistance I see on the drain. Okay, I've got a signal source in there, and that worries me. The Thevenin rules tell me I can short out voltage. I can short out a specific type. I can short out independent voltage sources. Dependent voltage sources, I have to do the weird V test over I test thing. But since this is an independent source here, for the purposes of finding REQ, I can short it out. For the purposes of finding the gain, I would have to leave it in there. So pretty much what I've got here on the drain is I see RS in parallel with RSIG. Okay. I think this has shown up on an exam somewhere in the past 5 years. REQ for most of the problems in these slides have. REQ5 is basically what I see looking into the drain of the transistor, REQ4, in parallel with that RD. Most, at least over half of the problems, I want to say at least 3 problems on the exam, are going to require you to know how to figure out these equivalent resistances. So pay attention to this. And I say this now, and people don't believe me, and then after the exam, they go, gee, I really wish I understood that equivalent resistance thing.
And most of the homework is separated values, like we are.
Yeah, I mean, on some of them, I give you values for little RO and values for GM and things like that. On at least one problem, I'll ask you to calculate GM and RO, but I'm not going to make you do that like every step on every problem. There's just kind of like mixing that up a little bit. Okay. Yeah. Okay, somebody's talking to me very silently. Can we go over the pre-lecture quiz? Let me get through these slides, and it's actually easier for me to deal with the pre-lecture quizzes if you send me an email. But I'll try to look at it at the end of class. The reason why is when you send me an email, I can actually look at what answer you've given and what the numbers were on the problem. And I can kind of figure out what you did wrong. So we'll either go over it at the end of the class or just send me an email, and I will take a look at what your answer was and figure out where your difficulty was. I want to get through these biasing circuits because I am still a little bit behind. It's not a huge, we got 10 more slides. That doesn't sound like a lot. We want to look at, so for these amplifiers, we've got to have a current source. We can't use resistors, we're using transistors. We're going to look at a couple of different schemes for how we're going to do that. This is a differential amplifier. My signal is coming in on VG1. It's the difference between VG1 and VG2. This is my output. These two transistors right there are the gain transistors. The ones, this transistor down here is a current source. And these two transistors up here are called an active load. They're basically acting like the resistor. So they're providing current. I have done this before. I've given you a big ugly schematic and I just say which are gain transistors and which are current sources. And if you say the active load is a current source, I'm okay with that. Because it is, it's sourcing current. It's also absorbing power. An ideal current source has a infinite resistance looking into it. In the case of this current source right here, the resistance looking into the current source is the resistance looking into the drain of M5. So RCS is RO5. There's not a lot of ways other than processing that we can change what that resistance is going to be. We could, any suggestions? See if anyone paid attention last class. We could put a second transistor in series with it, and we can make that input resistance bigger. That's probably the best thing we could do right there. M5 is the one that is going to determine the bias current. These will take whatever current that I5 has and drop enough voltage across them to keep that current constant. So that's why they're more like a load than a source. The way we build current sources, this is inside integrated circuits. This is what we call a current mirror. What I do here is I put a reference current into the IC, or I have a reference current coming from an internal DAC on the IC. And this current is like, in this case, is 20 microamps. It's given. And when I put that in there, I've got IREF going into there. The current, this current right here is 0, because there's no place for the current to flow. It's just going into the gate of these two transistors. So all of that 20 microamps has got to be going into ID1. If we know ID1, we can find VGS. We can use that to calculate VGS. The VGS of Q1 is going to be the same as the VGS of Q2 because they have the same gate voltage. They're tied together, which means the current ID out here should be the same if these two transistors are sized the same. And we went through this calculation once before. What we found is, okay, so the W over L of 1 is 50 lambda over 5 lambda. And I'm just going to reduce those fractions and call that 10. The W over L of 2 is 150 lambda over 5 lambda. I'm just going to call that 50. So Q2 is 5 times bigger than Q1. A quick shortcut on the math is if their size is 5 times bigger, and they have the same VGS, the current's going to be 5 times bigger. So this is going to be 100 microamps. I could go through and spend a lot of time on the calculations, but that's pretty much what happens. And I think you got to do that on the homework, so that should be okay. Now, another thing I got to worry about other than the current is if the current source transistor goes out of saturation, it basically stops working. So I want to find the minimum voltage right here to keep this in saturation. Remember, it's what VDS is greater than or equal to VGS minus VT. So the minimum value, VDS equals VGS min minus VT. I could say that VDS is VD minus VS, and VGS is VG minus VS, and then add VS to both sides of the equation and get VD min is VG minus VT. So we've got the gate voltage. VGS is 0.60. The sources are referenced to ground, so VG is 0.620. And VT is 0.373. That's given. So we get the VD min is going to be number 16 is 0.247 volts. Which means there is I've referenced the circuit to ground. I can't get less than 0.273 volts out of this thing before it stops working. Instead of having my output range going from rail to rail, going from 1.2 volts to ground, the output range is 1.2 volts to like 0.247 volts. And a lot of op amps, a lot of analog circuits, they will specify that, oh, you can only get within a volt of the power supply. You can buy rail-to-rail op amps and things like that. But when they say rail-to-rail, that doesn't mean you can go all the way down to ground. The best ones I found are like 50 millivolts above ground. And they start getting gain inaccuracies and things like that when you get close to the 50 millivolts. So yeah, okay, never mind. My analog aside. Okay, we got the minimum value of V out there. What do we want to do here? Now, in reality, we do have channel length modulation. It doesn't really scale exactly like this. I don't even think I even put this on the homework. But because of the slope, the 1 over RO of this line in the saturation region, you get another factor there. It's just kind of like the multiplier on the saturation equation of 1 plus lambda VDS. Now it's 1 plus V out over VGS over VA2. The only thing interesting about this problem, I think everybody can plug these things in. The only place where I could see people having problems is finding out what VA2 is. VA2 is going to be VA prime times the length of the transistor. Well, then I go, okay, that doesn't look hard. I'm going to start plugging in numbers, and this is where people get confused. VA prime is 20 volts per micrometer. What is L? L of 2 is 5 lambda. Okay, so now I have to go back for the process and figure out what lambda is. It's usually written on the front page of the exam, or it's if it's not an exam, it's in the TMSC 018 file. A typical value of lambda, and it's not given in this case, but it's usually given somewhere, is 0.09 micrometers. Because this is in micrometers, it cancels out that one. You don't have to multiply by 10 to the minus 6. It's just 0.09. So 20 times was it 0.5? 5 lambda. 20 times 5 lambda would be 100 times 0.09. I can do that one in my head. Would be 9 volts. I believe I did that calculation correctly. So that's the only part of that slide that's kind of difficult, and I see people asking me questions about that all the time. Now we go, this is an IC amplifier, and I've got one reference current. This is my golden reference current, and I don't care if it's exactly 20 microamps or whatever value that it is. I just want to make sure that everything is scaled linearly from that. If it's 21 microamps, I'm fine, as long as everything else gets multiplied by or divided by that 21 microamps. One reference current to rule them all. Now, for the current sources, they're going to have to be current sources for a circuit. And they're supplying voltage, they're supplying current from V plus. So right here, okay, good. It's just this annoying thing. Oh, pencil doesn't write that well. Ah, yeah, okay. I think I may have a handle on that. Okay. There's a little button on the side of my stylus. That may be important. The ones that are, okay, so this is a reference current. This M1 is a reference current. I don't really care what the value is. M2, if we look at that, it's sinking current because it is taking the current and directing it down to V minus. So M2 is a sink. M3, this is just converting from the sink to the source world. These are both references. I'm not actually supplying current to any amplifier with those. So I'm going to treat them like they're references. And the diff amp is now sourcing current off of the positive supply. So this one is a current source. The next slide doesn't make sense without explaining this. So I've got 3 reference transistors. They're all acting as current source types of things. The rest of them, the transistors in here are gain transistors, and the gain and the transistors in the other diff amp are gain transistors. At least some of them. So the next part of this is I want to just design the circuit, figure out what currents I want everywhere. Now the design constraints I'm given is the source needs to be 100 microamps. So M5 is 100 microamps. That's my source. The sink is going to be 50 microamps. So this one is 50 microamps. Okay. The rest of them, I got to keep the ratios. To get accuracy on the ratios, it's best to keep them kind of close to 1:1. And the limits on that is I'm going to scale them at most 1/5 the size or 5 times the size of the ones next to them. And we want minimum power and transistor sizes. So to get minimum power, my reference current here, well, I got to feed 50 microamps off of that. I want the lowest current possible and scale these transistors 5:1. So I'm going to put 10 microamps in here. So the W over L ratio, if I make M1 1/5 the size of M2, which is my limit on that, I'll have 10 microamps going through there, which is the minimum current. Now, over on this side, I'm going to have to do a 5:1 ratio between M4 and M5. I can scale M4 also down by a factor of 5. So I can make this 20 microamps. And M3 is going to have the same current. So that better be 20 microamps too. And it doesn't, and when it going from 10 to 20 is just a factor of 2, so I haven't divided or done my design rules. So if the W over L of M1 was X, this one would be 5X. This one right here compared to X has twice the current, so it's 2X. This would also be the same size, 2X. And going from 2 to 20 to 100, this would be a factor of 5, so this would be 10X. And we can figure out what size to make our transistors and get all our currents right. Okay. And, right, we just did this. The RCS, looking into, this is my current source right here. And the resistance looking into that is R05. The biggest effect I can have on increasing R05 is putting a second transistor in series with it. Then I get the multiplication. I get the R05 times 1 plus GM5 times whatever transistors RO I put on the source. So in order to improve the classic current mirror, we've got 2 different things we can do, and I don't want to. We can put, I want to go straight to this. We can put 2 transistors in series. So if we find the resistance looking into the drain of M2, this should be old hat by now. This is just little RO2. If we want to find the resistance looking into M3, it's going to be RO of 3. It's looking into the drain of the transistor times 1 plus GM3, and then off of its source, I see RO2. Let's stick some values in there. I'm going to do this slightly out of order so it makes more sense to me. If RO2 and RO3 are 100 k ohms, then we know that the resistance looking into here is 100K. And we could plug in numbers for our looking into M3, would be 100K times 1 plus, what's GM3, 800 microamps per volt, times RO2, which is also 100K. And when we calculate this, we get 81 mega ohms, I believe, 19. 8.1 mega ohms, sorry. Quite an increase. I've increased the resistance by a factor of 81. I've made that current source 81 times more perfect. What could possibly be bad about this? This is where we look at part B. So part B, what is the minimum voltage to maintain saturation? Well, for saturation, we just did this earlier, VD min is VG minus VT. The gate voltage here, we're given in part E, is 0.6. So I have 0.6 volts here. For transistor 2, my minimum voltage is going to be 0.6 minus VT is 0.4, 0.2 volts. That's for a 1 transistor current source. Now this has got to be 0.2, which means to maintain a VGS of 0.6, I need 0.8 volts on the gate. Now for transistor 3, it is VG 0.8 minus VT is 0.4. The minimum voltage is 0.4. So I've lost a little bit of headroom on my signal swing. I can only have my output voltage of the amplifier go down to 0.4 volts instead of 0.2 for a single transistor. Okay. That may be an issue. You have to look at your design requirements. Oh, yay. Oh, gosh, are we actually going to get out early? Now, the difference between, you're going to say this looks an awful lot like the last slide. This is called a cascode current mirror. And when you're doing a cascode current mirror, you basically have the strap between VD and VG both on the reference side of the circuit. The only change I'm going to make is I'm moving the strap over here, that was over here, over to this side. And this is called a Wilson current source. People thought it was different enough, they gave it a different name. They named it after Mr. Wilson, not Mr. Cascode. Sorry. Same thing we've got going on here. Resistance looking into M2 is going to be 100K, just like it was before. The resistance looking into M3 is still going to be 8.1 meg. It hasn't changed, so I don't see any differences here. The biggest difference is when we look at the minimum voltage for VD3. So if I have a VGS of 0.6, that's telling me this is 0.6. My minimum, I did this wrong. I just resolved this today. My voltage at the drain, because I've got the strap there, has also got to be 0.6 volts, right? My VGS has got to be 0.6. which means this is 1.2. Oh, this is horrible. And my VD min right here is going to be VG minus VT is 0.8 volts. I've lost a whole volt of headroom, almost 0.8 of a volt of headroom. I cannot get my amplifier output below 0.8 of a volt and have it maintain its linearity. So in my opinion, the Cascode's better. The Cascode, you get a little bit more voltage drop. The Wilson, you got a much bigger voltage drop. And you have the same increase in the output resistance of that current source. So it's more ideal. So wow, how did this happen? We're gonna look, okay, yep, go ahead, questions, and then I'm gonna go look at Chris's thing.
Yeah, was there an actual advantage to the Wilson, or was it basically don't do this?
I would say don't do this. I can't see an advantage, but there may, I don't know, there may be a frequency response advantage or something like that. If your senior engineer, who you'll be like following around when you start working, tells you to use a Wilson source, it may be a good idea to just say, but wouldn't it be better to use a Cascode because I would have more headroom? That would be a very reasonable question to ask, and then he would tell you the answer to it, or she, whichever one. Yeah. But I can't see an advantage based upon this analysis for the Wilson. Okay, any other questions before we head for the pre-lecture quiz? I'll have to wing it this time because I can't call up the grade book to do this. Okay, so let's look at the pre-lecture quiz. What am I looking for? I'm looking for EE Learn. Sign in. Oh gosh, it's going to do the duo thing, isn't it? I do have my phone with me. No, I got it. I can go on that one. 380. Now my phone can never leave my side. I can't work without my phone. And they don't buy my phone for me, and they don't pay for my phone for me. Yeah, I would need lots of fobs. That would be the problem. Content. You know, back in, I can remember not that long ago, it was considered to be pretty standard practice in industry. If you were required to take messages on a phone, they could not use your personal phone number. They could not use your personal cell phone number. I knew one guy, he had 4 different cell phones. And it was basically, because you're using your minutes and you're using all this stuff for work, basically. And you're using your data for work. And so he knew that basically it's 8 o'clock at night. I'm not answering that phone, or that this is the emergency line that I have to answer, even if it's 3 o'clock in the morning, and all those different things. So I don't know. You just keep kind of like chipping away at the line between your work life and your home life. Now you have to use your own phone, because who wants to carry 4 phones around? It's for your convenience. Yeah. Right. And you know, it was like certain times of the day, you know, like you're going out at night or something like that, you knew which phones you could leave at home and just let them ring. And I'd rather be able to do that than have to be tied to my phone all the time. We're in part 2. Pre-lecture. Let's see, which pre-lecture was it, Chris? Oh, okay, you're chatty. 22C. Okay, good. That will narrow it down a good bit. 22C. Okay. Let's start this one and begin. Okay. Which problem it was? Okay, Yeah, you're back behind there now. Let me do this. That works better with my finger. Let me check my notes. So the first one's a diff amp problem. The second one's a diff amp problem. The third one's a diff amp. Yeah, there's lots of diff amp problems. Oh, yeah, we'll get to that. Okay. Let's see if I can get it right. So let me look at these. You're given the GMs, you're given the ROs. What is the output resistance? So for question 1, oh, the one for common mode gain and common mode rejection ratio. Okay, common mode gain is, so they gave you basically, let's see if I can write on this, probably not. They gave you the common mode gain is 0.00058 volts per volt. The common mode rejection ratio, and part of these pre-lecture quizzes is getting you guys to read ahead a little bit, and this will be in the Cedra book. But what common mode rejection is I know this on this level. Where's my paper?
You said to take your common mode gain
Yeah.
by your differential,
Right. And then let me do it on
In
here.
this case, it wants the logarithmic scale.
Right, so you've got what common mode rejection ratio is defined as being the differential gain over the common mode gain. Now with these differential amplifiers, the goal of these things is to get the differential gain high and get the common mode gain low. So you're given numbers for these. One was like 0.85 and one was 0.00058 or something like that. So that's all the common mode rejection ratio is. And this it would be in volts per volt over volts per volt. Or we could just call it no units. Okay. Defined it in dB, which is the most common way of speccing this on data sheets. All you do is, it's a voltage gain, so I'm going to put 20 out front, times the log of CMRR. And then the answer comes out to be whatever that is in dB.
Hey, Julie.
Yes.
So I don't know if you can hear me. I'm on a different computer. So
Yeah, I can.
That question was actually a bit of a breeze because they gave us both of the numbers.
Right.
But there were 2 questions. One asked for the common mode gain and one asked for the rejection ratio as answers.
Okay, so the common mode gain, let's see, let me go back and look at that one.
I think it might have been 3 and 4, but I know each quiz is different.
For that one, the questions are going to be, oh, what is the common mode rejection? Okay, so then you go through common mode gain. So question 3 is asking you what the common mode gain is. In the 05 slides, there is a formula for common mode gain, and I don't know what it is off the top of my head. And it's probably also in the Cedra Smith book. And I could give that to you if I was sitting in front of my computer. But wait, oh, wait. Yes, I can. I can tell you where it is. If I go into, let's go back to the end of days. It was 05. So we can do like the 05. Did all that in one day last semester. Boy. Okay. In these slides right here, which are already posted to BB Learn, and I'm going to move you guys out of the way. DC bias, MOS differential pair.
I think in the slides, that one was around number 15 or 18. For that.
Okay. So VCM, MOS different limits of ED. It's in here somewhere. the gain formula, differential input, common mode, rejection, common mode signal, RT mismatch. Okay. Oh, great. Where's the common mode gain? I can't write. I never remember this.
Is it not the RD over URS?
RD over 2 RSS. That sounds familiar.
I think that's right.
I was able to use number 15 for the rest of those problems.
Number 15. Let's see. Let's look at this.
I'm sorry, not slide 15, but the number in the top left.
Oh, thank goodness. Okay. There's a reason why I did that. 15. The common mode rejection ratio is just AD over AM, but I don't have an expression for AD and AM yet. Oh, there it is. BO1, the common mode gain is RD over 2 RSS. Is right there on that slide. And the common mode gain and the differential, wait, we can do this. The common mode gain is RD over 2 RSS. I'm gonna write that down. RD over 2 RSS. And the next thing we have is the differential mode gain should be GMRO. So we get the RD over RSS. Yeah, and the differential mode gain is GMRO. And when you divide the two, you get the common mode rejection ratio. This is with a mismatch, though. See if I can find one without the mismatch. No. Okay. So between those two, you should be. And RSS is what RSS is going to be. Normally, I have a transistor here. Is just going to be the RO of that transistor, looking down, if you're trying to calculate what RSS is.
So should we expect our common mode gain to be a really small number or a really big number?
You want the common mode gain to be a really small number. And you want the differential mode gain to be a really big number. Now, let me explain to you why it's like that. Now, and the ratio of the two is the common mode rejection ratio. And if you buy amplifiers, it's typical to see a common mode rejection ratio at midband of 100 to 120 dB, like 10 orders of magnitude bigger than the other. If I have a differential amplifier, like an op amp, I want, if any voltage that's common to both of these terms, my signal, let me do it this way. The signal voltage is going to be the difference between those two inputs. And so coming in here, I have V common and V differential. And over here on this input, I have V common, and I've got like, okay, make this one negative, make this one positive, VID over 2. So part of my signal's coming in from there. The common mode signal is generally consisting of noise and pickup that you're getting on your lines. Because if you think about the negative terminal as being ground, if there's any common signal between your ground and your signal, I mean, it's literally both of them are bouncing up and down together. You want to reject that. And what this common mode rejection ratio is it gives you a way of rejecting the noise, filtering out the noise that's common to both of the inputs, and only amplifying the difference between the two signals. It's great if you have long lines, if you have big long cables between your equipment and your measurement device. And that even happens in the lab. I mean, I used to think of big long lines being tens of feet when I was in astronomy, or even hundreds of meters through a telescope. But when you're doing really sensitive measurements, like we're measuring stuff down at the nanoamp level in the lab, you know, 2 or 3 feet of cable is enough to give me enough noise on those lines that having a differential input, rejecting that noise really helps you out. And then there's even a whole other thing level of that with 4-wire measurements. But it's just, it's a good practice whenever you have a board where you're taking an analog signal into that board, is to put a differential buffer on the front end, not just a buffer, a differential buffer, to get rid of any noise and pick up between what the source was and what your receiver, what you're using on the board. Yeah. And
Do you think you'd be able,
what?
would you be able to put the quiz back up, maybe not for points, but just so I can retake it and make sure I get the concept down?
Sure, I can do it. In fact, I'll do that right now. Because if I don't do it right now, I'm going home and I will forget. I will turn off my work cell phone. Let's see. So I'm just going to say save and submit. Yeah, I know I didn't finish it. So let's see. I gotta find my buttons. Okay. And 22C, and I will do this for like everybody. What else? Oh, great. Wait, just this
I was also wondering about 22V because I got like 3 out of, I think 3 out of 9, 3 out of 12.
Okay. Right. If you're having problems and you're taking the exam, if you're taking the pre-lecture quiz, you can send me an email right then before you use your third attempt, and I will look at it and take care of it if I'm not in class. Okay, so you're gonna have. I have. You're right. Canceled. Okay, so 22C. I know there's too many quizzes in here. 22C is this one right here. Oh, I didn't want to do that. There's too many buttons in my. I want to do this one. Edit the test options. And this will do it for everybody too, if everybody wants to go back and retake it. I'm giving you, first of all, 3 more attempts, and it will display until end of day. And the due date, I have to change that to, otherwise I go a little yellow arrow, end of day. Okay, so there you go. That is 20.
Actually, I also had questions about the other one due today, 23C.
23C, where is that? 23C, so this is right. And you can see it's available now. So let's look at this one. Yeah, and really the best way to ask questions on the pre-lecture quizzes is to send me an email while you're doing them, because I can look at what your former answers are and figure out what you're doing. Okay, so which one was this? 1 or 2 or 3 or 4?
I got number 3 was fine because you're just subtracting V1 from V2.
Okay.
And then the other 3, I thought I was going in the right direction, but I just got the wrong answers in all of them.
Okay, so a MOS differential pair with a resistor load has an overdrive voltage of 0.225 volts. That's VOV. And a mismatch in the drain resistors of 1.9%. What is the V offset due to this in millivolts? And again, I'm going to go back to those 05 slides. Where are they? Right here. The common mode gain. So I have an RD mismatch, And RD mismatch is going to affect, that's how it affects my common mode rejection ratio. I have a GM mismatch. Where's my DC bias? Common mode ratio. Okay, so we're back away from that. Yes. Yeah, it could be, you know, 0.01% or whatever it is. GM mismatch. Basically, okay, if I have any kind, it turns out if it's basically any kind of mismatch I have, it's basically the same thing. I am going to get my delta RD is going to, let's see, my common mode gain before was RD over 2RSS. You multiply whatever the old offset voltage is by the percent difference. So delta RD over RD is going to be like a 1% mismatch, would be 0.01. So you would, your variation is going to be your common mode gain plus or minus that 0.01%. So both GM, it doesn't matter whether it's GM, everything's going to get multiplied by 1% if it's a 1% mismatch.
I think I saw a note on slide 36 that was relevant.
Okay. Note on slide 36.
Or was, I don't know, it might have been before that, but it was about the mismatch percentages and how to do those.
Yeah. Yeah, so this is plus and minus 1% GM mismatch is going to cause the common mode gain to increase by basically 1%. A 1% mismatch on GM is going to be the same thing.
We were given a voltage for that quiz question. I'm just wondering where the voltage actually comes into play for that equation.
The voltage, it's not directly from the, if you want to see, you'd have to dig into the Cedra Smith book for that, but any kind of mismatch, whether it's RD or GM, is going to cause a mismatch in the offset voltage. The offset voltage is the differential voltage at 0 volts on the output.
I think the quiz mentioned an overdrive voltage, and we had to use that somewhere as an input. I'm wondering if it's relevant at all, because we were the value.
Well, the overdrive voltage is just VGS minus VT.
Can you go over to the quiz?
Okay. And again, if you ever have any questions on the pre-lecture quiz, email me when you're doing the quiz. Because I don't even look at these most of the time. The easiest way for me to figure out what's going on is to look at what answer you gave and compare that to the answer that's expected, and I can figure out, while I'm sitting there looking at my computer, I can figure out what's going on and tell you where your error is. Not knowing what your answer is, and I can't call that up right now because I'd have to call up your gradebook report, and I can't do that in class.
Oh, you number 1 on this quiz.
Yeah. Okay. Yeah. See, I don't know what you did. The overdrive voltage is VGS minus VT. It has a resistor load. It has a mismatch in the drain. So the VOS would be the difference. It would be 1.9% of 0.225. So 0.019 times 0.225. And then you put it in millivolts.
Okay, I think what I was doing was I found some other textbook that said I should be dividing overdrive voltage by 2 and then multiplying by the percentage we were given.
Okay. Well, it gets multiplied by 2, it gets divided by 2, but then there's 2 halves of it and they get added back together. Okay,
And will you also be putting this quiz up for the rest of the day?
sure. Let me go back. Okay. And again, and you know, just again, it's if you're having trouble with the pre-lecture quizzes, the most efficient way is just email me while you're taking the quiz, and I can help you with that in real time unless I'm in class.
Before it's due, right?
Yeah, it's helpful if you do it before it's due. If it's right at the due date, I will extend the due date. Sometimes I look at your answer and I say, okay, this is a reasonable thing. Sometimes it's just rounding, and rounding errors is enough to give you 0 points. And if I can check that against there, I just give you credit for it. If it's just a rounding error. That happens all the time. Let me see who's here, because I have a lot of people missing. I'm going to stop my share. And I have, who's new? Let's see, Gabriel Balderrama is not here. Danielle is not here. Sigwy is here. Mouse is not here. Victor is not here. And Chris Weber is here. Okay, I got the roll. And it is the 11th.
I just saw Victor leave. He's here.
Okay,
He left like a minute ago.
he was here.
Yes.
Okay, good enough. Okay. All right. I will see you guys on tomorrow. Where's my?
Thank you,
Okay.
Julie.
Okay, I'll see ya. Put my mask in my.
Wait, Julie,
Yeah.
can you do a sample problem of the CMR? Because I don't understand the change of delta of GM over DM in general. Do you divide it by 0.01 if it's like the change is 0.01?
You would take the, you would, yeah, we'll do that in class next week. And we don't have any more pre-lecture quizzes, and I am drained right now.
All right.
So either get a hold of me tomorrow during lab, or we can, or just call into office hours or some other time.
Yeah, because I totally bombed the pre-lectures and I'm
Right.
still confused on them. So
Okay.
and my thing glitched out during the explanation of one accidentally.
Yeah, you just pretty much, it degrades it by, you go into those 05 slides and look at those formulas. You're basically just multiplying by the % of change of anything.
And they have the samples on there too?
They have the sample what?
Like examples
Oh,
of
example?
the problems. Yeah.
There's
Okay.
probably more
Yeah.
examples in the textbook, in the Cedra book. All I've got in the slides are just the GM and the RD. But pretty much all of them, your mismatch gets multiplied by what it is, and that gets added to it. Okay. All right.
All right. Well, thanks. Bye.
Okay. We'll see ya.